Okay, students, let's, I messed up. Sorry about that. Let's talk about momentum a little bit, okay? All right, looking at impulse. All right, I don't know if you've ever noticed during collisions that at the moment of collision with an object, and here they're using a soccer ball, and that's a good example. You could use a kickball, football, baseball. But at the moment the collision occurs, you're going to have a very brief time interval in which the object will compress and then contract, okay? Now, the duration of this time period, how long it takes, will of course depend on how fast the object is moving when it makes the collision with whatever it's going to collide into. So if we take this situation here, and a good way to do this, you could video this with your camera or with a GoPro, and then take the video clip and place it into Logger Pro, and then we could analyze the motion. Logger Pro is very useful software we use, and we could look at what's called the impulsive force from the beginning to the end of the contact. And of course, during that time interval, we would see the maximum amount of force achieved by the foot colliding with the ball. Now, what we can do, if we graph this, we can actually integrate all of this area, because when we look at impulse, impulse is actually the integral of the force with respect to time. So we integrate the area under the curve, and we can determine what we call impulse, okay? Now, in this case, we'd have to integrate it because it's not a nice square or a nice rectangle. This would have to be integrated. However, if we took this particular situation where it was 0 and then it went straight up to a particular force, came over during the time interval and come right back down to find the area, that would be easy. We could just take the area of the rectangle and find the actual impulse that occurred on this object, okay? Now, so you should remember that the impulsive force is directly proportional to the area under the force versus time curve. And so we call that the impulse J, okay? That's what it's called. The impulse is called, the symbol is J. Okay, now, the best way to look at your forces involved is to look at what we call the average force, okay? And of course, that's the constant force that has the same duration, delta T, in the same area under the force curve as a real force. So typically when we define impulse, this is how we do it mathematically, okay? So we just say that impulse J is the area under the force curve, and of course that's force versus time. So we can, in other words, it's what? Say we multiply the force times the time, because look, that's the area, the force, the force right here times the time, okay? That is impulse, okay? There it is. Now, what are the units? Well, they have the same units as momentum, as we'll get to here in a minute. Now, typically, though, we will write it, instead of saying kilograms meters per second, we will say a Newton second. And why do we do that? Because force is in newtons and times in seconds. But when you do the math, we've got kilogram meter per second squared times a second, and that gives us kilograms meters per second. So we could write it that way, but typically when we're talking about impulse, we're going to write it this way, Newton seconds, okay? And it is a vector quantity, okay? So the direction does matter, okay? Direction does matter here. In other words, it's a vector quantity, not a scalar quantity, okay? All right, let's look at this example. We got a rubber ball experiences a force shown in the figure there as it bounces off the floor. What is the impulse of the ball? What is the average force? Well, the best way to find the impulse here would be to do the right triangle method. But remember, it's the area under the curve. So the impulse is what? 1/2 the base times the height, right? So the impulse will be J is equal to 1/2. The base is 8 milliseconds, so half of that would be what? 4 milliseconds, and that's to the, excuse me, I'm writing it wrong. I went ahead and made it half, didn't I? My bad. The base is 8 milliseconds. There we go. All right. And then times the height, which is 300 newtons. And so what are we going to get? Okay, well, we'll look here in a minute. What would the average force be? Well, look, y'all, do the slope of the line. You could do it either way. All right, we got 300 to 0, so 300 minus 0 is what? If you do the slope calculation, 300 minus 0 is 300 divided by 2, or times 1/2, and you get what? 150. That's real easy. Okay, so here they're showing you how to work it. And so what do we get? We take and work it, and notice what we get. 1/2 times 300 times 8 milliseconds, and it gives us what? 1.2 newton seconds. Now part B, the average force. Now they use the impulse equation, and that's fine. But you could also work it the way I did it too, because it was a straight line, okay? So yeah, use your impulse equation, okay? Find the force average. All right, neat, eh? All right, momentum and impulse momentum theorem. Momentum and the impulse momentum theorem. Now, okay, anytime objects collide, they have an initial velocity and then they'll have a final velocity. For example, if the puck's sliding along and then you hit it, and this is looks like a hockey puck, then you hit it with your hockey stick, you apply force to it. Well, guess what? The final velocity should be greater than the initial velocity. Why? Because remember, force is what? ma, isn't it? In other words, you have acceleration, and you have acceleration, you have force. Guess what else you have? You have changing velocity, because what is acceleration? It's delta v over delta t, isn't it? Right? So it should increase its velocity, and of course we know it does. So again, we can find, and here this is just kind of a review of how we can find, taking Newton's second law and what I just wrote. This is the same thing, okay? It's just written with respect to acceleration, okay? Here again, I just showed you that, and we combine these two equations. What do we find? Well, look, right there, which is basically this right here, right? Now, so when we look at we take impulse, and what is impulse? Impulse is what? The force average times a change in time, right? So when we set it equal to, when we take those two equations and put them together, look what we get. We get impulse is equal to the change, that is change in, final minus initial, momentum. So we can derive from this to say that what? Momentum of an object, p, lowercase p, is the product of an object's mass and its velocity, okay? And it is a vector quantity. It's a vector quantity, okay? So direction does matter. Very important, all right? Direction does matter. So that's how we define momentum. So I hope you're writing these equations down. We wrote the impulse equation. There's the impulse equation. Here's the momentum equation. Now, we can take these two, all right, and again, that's just basically what I've already said. Impulse, momentum, falling raindrop, that just kind of gives you an idea of some various things. Now, okay, so when we look at the equations of impulse and relate it to momentum, what can we say? We can say then that what? That momentum, that impulse is equal to the change in momentum. In other words, what are we saying? That it is the time interval at which a force is applied, an average force is applied. Okay, because remember, what is impulse? Okay, so we can write it this way too. Okay, that's a lowercase p. We can write it that way. And so what does that mean? That means that momentum changes in relation to the force applied to the object during a given time interval. Okay? All right. So what will that do? Well, of course, that causes a change in momentum. All right? When you apply a force, it's what I'm saying, basically. It causes a change in momentum. So changing momentum is related to what? The force applied during a given time interval. Okay? Now, here's other ways we can write it. We can break this down. Impulse is equal to, well, mv final minus mv initial. We can write it that way, okay? And it's, look, the only thing that changes in the y direction is you change x to y. That's the only thing that changes, okay? Oh, and of course, the units for momentum, they should have listed it right here. Yeah, here it is. The units for momentum, we don't want to forget that. Sometimes I'm bad to run off and leave the units. There's your units, kilograms, meters per second. That's very easy because, look, you should figure that out on your own. Kilograms and meters per second, okay? All right. Sorry I run off and left you there. Okay. All right, we got a force pushes a cart for 1 second starting from rest. To achieve the same speed with a force half as big, the force would need to push it for how long? Well, okay, if it has a speed at 1 second and then you want to keep that same speed but with a force half as big, well, guess what you got to do? The time interval. You got to double it. Yeah. Okay, that's a good little sample question. All right, and here again, just showing you that the impulse momentum theorem tells us what? That the changing momentum, that the average force is equal to the negative of the initial momentum divided by the time interval. All right? So the average force needed to stop an object is inversely proportional to the duration of the collision. Now, what the heck are we talking about here? Okay, look. If the duration of the collision can be increased, the force of impact will be decreased. Now, what are we saying? All right, look, y'all. Notice the relationship here, that force and time are inversely proportional to each other. So, for example, if we are in a car and we run into a tree, okay, well, guess what's going to happen? You're sitting here and your head's going to go forward, isn't it? Yep, it sure is. Well, what can we do to decrease the force of the impact? Now, please understand something. I know that Newton's third law says that F of 1 on 2 is equal to the negative of F of 2 on 1. Well, what do you say, Mr. Shields? The forces at impact are always conserved, okay? We're not violating Newton's third law. What we are doing here is we are increasing the time interval so we can decrease the application of that force. In other words, we're not doing away with the force, we're just spreading it out over a much greater time interval. Okay? Okay, so how do we do that? Airbags, seat belts, airbags especially, seat belts too. So airbags, that's when you have a collision, that airbag inflates, and what does it do? And I mean, it's just in a matter of probably milliseconds, okay? It inflates very quickly. That's why they use an explosive charge, and I think the gas that inflates it is nitrogen, which is inert, basically air, okay? And they use an explosive charge, and that's why, because they want it to inflate very quickly, okay? So it catches you, your face hits that airbag, and it increases the time interval between the collision and you hitting the steering wheel. And that causes a decrease in the impact force, okay? All right, I hope that makes sense. That's why we use airbags. Okay, now here again we're looking at this is just kind of a diagram just to kind of review momentum and impulse and the relationship between the two. Remember that impulse is changing momentum, okay? How much change in momentum did we have when a force was applied to the object, okay? Now, total momentum, now I don't know why they used a capital P. I do not like that. Let's keep everything like it's supposed to be. And just write down here P total. What's wrong with that? Why can't we do that? Well, y'all, come on. P total is going to be P1 plus P2 plus P3 plus P4, dot, 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 and on and on and on and on, okay? So, if you have a cue ball, when the cue ball, if you have one ball hits another one, and these two are motionless, well, guess what? If you, when this ball hits these two, they should go off in the same velocity. They may just go off in different directions based on the angle at which the ball hits those other two, okay? All right, now why would they go off the same velocity? Because they're sitting still, okay? They both should have the same velocity. And by the way, since they're both the same mass as the other ball, their velocity should be half what the initial velocity was of that ball that hit them, okay? All right. All right, of course, as this is again just kind of a way to set up the problems. You always draw it. You establish your coordinate system. What does that mean? That right there. They list your known information and to identify the unknowns. That's just kind of a little thing there to help you on that. And that's good, okay, if you want to look over that just to kind of remind you, oh yeah, I need to do this, I need to do this, okay? You always draw, and if you've been watching me in these problems, I always draw it. I label the parts. I write down the knowns. I write down the unknown and put a question mark by it, okay? That's the way you need to do all your problems, all right? Now, again, let's look at conservation of momentum. All right, let's say we got two balls moving towards each other. They're in straight line with each other, and they collide. They have the same mass. They have the same speed. Well, guess what's going to happen? They're going to collide, and they're going to move away from each other with the same speed in the opposite direction, okay? So nothing should change because now if their masses of one is greater than the other, well, that's going to be a little different story, okay? But anyway, we'll talk about that in a little bit, all right? So the momentum of ball increases. If the momentum of ball 1 increases, the momentum of ball 2 will decrease by the same amount, okay? Now, I don't know why they said that because both of these are moving at the same speed and towards each other, but if one was sitting still, it would then, okay? All right, now, what do we need to remember about the law of conservation of momentum? We need to remember that P final is always going to be equal to P initial, and we're coming to that, okay? In other words, momentum is always conserved. Now, what about energy? Well, we'll talk about that in a minute, all right? So, internal forces act only between the particles within the system, okay? That makes common sense because when they collide, that's the only interaction there's going to be. So the total momentum of a body is subjected to only internal forces. The total momentum of a system subjected to only internal forces is always conserved, okay? But why do they keep talking? They're trying to get you to understand, the author is, that momentum is conserved, okay? Regardless of whether it's elastic or inelastic, momentum is always going to be conserved, okay? All right, you awake in the night to find that your living room's on fire. Oh, dear Lord. Your one chance to save yourself is to throw something that will hit the back of your bedroom door and close it, giving you a few seconds to escape out the window. You happen to have both a sticky ball of clay and a super bouncy ball next to your bed, both the same size and the same mass. You've only time to throw one. Which will it be? Your life depends on making the right choice. Okay, so here we are. The house is on fire. Dear God, help us. All right, so we're going to throw which one? Well, we got our door over here, and we want the door. I don't know if I can draw it or not. Okay, we want the door. All right, here's the wall. There's the ceiling. All right, we're on fire. We want the door to close, don't we? Okay, so we're going to hit the back of the door. All right, well, let's think about it. All right, impulse is what? J is equal to delta P. All right, well, let's look at this. So we give the ball, if we're going to throw the ball, it's going to hit the door. The velocity will be what? Initial velocity. We're going to give that, make that positive, okay? All right, if we throw the clay ball, what's it going to do? So it's going, let's just say we throw it with a velocity of 1 meter per second, okay, and it's positive. If we throw the clay ball, all right, what's the final velocity going to be? And I always do this in my physics class. I didn't mean to erase all that. My Cal-based physics class, I always do this demonstration, okay? All right, if we throw the clay, what's it going to do? Okay, it's going here, and it's going to do what on the back of the door? It's going to go and it's going to flatten out, isn't it? The final velocity is what? 0 meters per second. Well, let's look at the impulse. So J is equal to what? Now, we're going to not worry about the mass. Mass is the same. So the final velocity is 0 meters per second minus 1 meter per second. So the impulse is what? A negative 1 meter per second, isn't it? In other words, that's what we want. We want a negative impulse. We want it to, shut the door, okay? We want the door to move in the opposite direction, right? Okay, we want it to close. Now, all right, what if we throw the super ball? We throw the super ball with the same velocity, same mass, and it hits the door. Okay, and it hits the door. And it's going to hit the door, but you know what? It's going to do what? It's going to bounce back, isn't it? With a final velocity of, now this is positive, now this one becomes negative. Remember, direction matters. Direction matters. You say, well, wait a minute. All right, it's going this way with a positive velocity, positive 1 meter per second, hits the door and bounces back with a negative 1 meter per second. All right, let's do the impulse. The impulse is change in momentum, so final is 1, negative 1, minus the initial, which is 1. So we get an impulse of what? Negative 2, we're going to say kilograms meters per second, right? I left the mass off because, why did I do that? Because they're both the same, okay? So we don't need to include the mass for this demonstration purpose. So we're going to get kilograms meters per second. Well, which one do I need to throw? Well, which one had the greater value? Well, the super ball did. So we're going to throw the super ball, all right? And I always do this demonstration in my classroom. All right. So again, external forces are now external forces are outside agents of the system, like me hitting a cue ball or me kicking something. That would be an external force. All right. Well, as long as the net force is 0, the total momentum of the system does not change. Okay. You do not have an change in momentum. Okay. Now, if I apply a force, if I give it a net force, then the initial momentum and the final momentum will be different, okay? But momentum is always going to be conserved, okay? Regardless of whether it's an elastic or inelastic collision, okay? Now, okay, so what does the law of conservation of momentum tell us? That I've already said this, that the final momentum is equal to the initial momentum. And by the way, that should be a lowercase p, okay? And of course, don't forget it's kilograms meters per second, okay? All right, now, so here they're just showing you how we would write it, that P final, and it doesn't matter how many systems are involved. We could have 20 systems. Well, guess what? This going to be, a final is going to be equal to the initial, all right? Now, okay? So how do we work these problems? Again, this is just good ways to set them up. You always clarify and define the system, okay? Find out if it's an isolated, in other words, net force is 0. All right, and then of course you set your equations up, okay? Now I'm not going to read over all this, you can read it, all right? All right, so the goal is to choose a system where momentum will be conserved, okay? So I would choose, that would be my system, cart, we choose a person, there's no non-zero net force acting on the system, okay? So we know that momentum is going to be conserved, all right? Now, what about inelastic collisions? An inelastic collision, perfectly inelastic, is one in which the objects stick together. And that's the key thing. They stick together right here. Boom. Okay. Now look, common sense is going to tell me, okay, which way will they move when they stick together? Okay. Let's say they both have the same velocity, but this one looks like the mass is twice as large. So which way are they going to move? Well, duh, it's going to be moving to the right. Okay, why? Because this one has a greater, well, it also has a greater velocity too. All right, but if they both had the same velocity and this one with a greater mass, it's going to move to the right. Okay, all right. Two boxes are sliding along a frictionless surface. They collide and stick together. Afterward, the velocity of the two boxes will be what? Well, let's do the momentum. Momentum of this box is what? Well, 1 kilogram times what? 4 meters per second. So that's what? 4 meters per second. And it's which way? That way. Well, this one right here is what? Momentum is equal to 2 kilograms times 2 meters per second, which is equal to 4 meters per second, but it's in the opposite direction. I wonder what the final velocity should be. Well, one's 4 meters per second to the right, and the other one's 4 meters to the left. It should be 0, okay? Remember, y'all, direction matters. Direction matters, okay? Now, what about two-dimensional, looking at two-dimensional systems? Well, really and truly, nothing changes except you have to remember that your direction, the angle at which they strike, will come into play. And of course, what is that going to lead to? That is going to lead us to having components and solving it using the component method and using the square root of the squares, okay? All right, like we did back in some of the earlier videos on force, okay? All right, now, one other thing, too, about inelastic collisions we need to remember. Ooh, I almost forgot it. In inelastic collisions, momentum is always conserved. However, energy is not. Okay? What about perfectly elastic collisions? All right? Inelastic, now that's for inelastic. All right? Well, what about, and I forgot this, and I don't know why I didn't talk about this. I'm sorry. I was thinking about it earlier. Well, where is it at? Did they not talk about elastic? I thought we had a slide where it's perfectly elastic. Okay, I'm going to write it right here. If you have a perfectly elastic collision, guess what? Momentum is conserved always. Doesn't matter whether it's elastic or inelastic. However, energy is also conserved. Okay? So, perfectly elastic collisions, you have conservation of momentum and energy. Perfectly inelastic collisions, you have a conservation of momentum, but you have a loss, or energy is not conserved. Now, if you think about car crashes, okay, what is a car crash? A car crash is mostly an inelastic collision. Why do you think when you crash a car that the vehicle is deformed? See, some of that energy loss goes into the deformation of the metal and the plastic, okay? All right, angular momentum. Momentum is, of course, not conserved for a spinning object because the direction of motion keeps changing, okay? All right? So momentum is not conserved because you have a change in direction for angular momentum. The quantity, of course, that expresses this idea is called angular momentum. And how do we write that? Well, we take Newton's second law for angular acceleration. We know it's the torque net divided by the moment of inertia. And we can also find angular acceleration using the change in angular velocity during a given time interval. So when we put these two equations and rearrange them, if we put these two together, notice that if we put these two equations together, we get what? We get angular momentum is equal to the moment of inertia times the angular velocity, okay? All right, so and again, they just wrote the impulse momentum theorem again just to show you where it is really deriving from. So the quantity of the moment of inertia times the angular velocity right there is the rotational equivalent of linear momentum. All right? And notice that linear momentum the units of angular momentum is kilograms meters squared per second. Okay? Kilograms meter squared per second. Okay? Now here's showing you just the comparison. We're comparing rotational to linear dynamics. Of course, we know that rotational dynamics deals with torque. We cause motion. Well, how do we cause motion? And that's in a rotational manner. How do we cause motion in a linear manner? Well, we apply a force to it. Moment of inertia, okay, the mass, okay, depends on how the motion, how easy it will be to create or stop motion. Well, linear dynamics, okay, if you apply a force to an object but then you double the mass, guess what happens? Well, to move it at the same acceleration, you've got to double the force, don't you? Okay? Yeah. Okay? All right. Velocity, angular momentum. Notice how we write it. Okay? All right. So we can also write angular momentum this way. The change in angular momentum is equal to the torque net times the change in time. So if the net external toward object is 0, then the change in angular momentum is 0 as well. So if there's no net torque, then there's no change in angular momentum. So we can write the law of conservation of angular momentum, that the angular momentum of a rotating object subject to no external torque is constant. The final angular momentum is equal to the initial angular momentum. So if there's no net torque, just like if there's no net force, momentum is conserved. If there's no net torque, angular momentum is conserved, okay? And of course, we can write total angular momentum. I mean, come on, y'all. We can write L final is equal to what? L initial, can't we? So we can write them that way, just like we did with momentum. And I hope this has helped you to understand.